Hi, good morning, good afternoon, good evening, wherever you are, and welcome to the an overview of the Mechatronics. My name is Professor Bhaskar. I head the Department of Mechanical Engineering at Mahindra University, Ecole Central School of Engineering, and today I'll sort of give you an overview of what mechatronics is, what have been the trends, how it evolved, and then look at what does it require to to specialize in mechatronics, and what are the areas where there are opportunities to grow. Okay, and before I start, I want to acknowledge a few people. So Professor Deep Set is our mechatronics and robotics professor, and there are three teams: the autonomous underwater vehicle, and then we have the mu disinfectant autonomous robot team, and then the gas monkeys team, and the undergraduate student and IIT Delhi, because some of the material has been derived from the work of these people. And then I would also like to acknowledge some of the sources for image for better educational purposes, and to convey concept, and the images which have red outlines are our MU internal work, right? So if you look at the evolution of machines, right, let's look at the common daily thing about cooking, right? In the past, you used to have pans, pots and pans. You would heat using either firewood, now then evolved into gas, then into electricity. Um, then currently we are now into a bit of automated things where we have the rice cookers and other things coming up, driven by the electricity and a bit of controls and sensors, right? In the future, it would happen that you just put it up, and then the sensors would look at the color, and then the composition of the vapors that are coming, and then tune and check automatically, and then you would have a tasty meal out of the vessel, right? Let us look at another example of a camera, right? We keep taking a lot of snapshot. It evolved from getting the light to focus on photographic plates, and you go and develop it. Then it evolved into photofilm rules, and then okay, from there it became digital, right? But you still have the camera lenses, others actuated. There's a lot of control on how much of the exposure, right? And do you want in fast motion, slow motion, and the different varieties of technologies that came into this. So while cameras were evolving, phones were also evolving, right? You had the mechanical dials. From that, it went into the digital electronic button type systems, still corded. Then they become wireless. Now you could connect and talk to multiple people, right? So these both have been going in parallel. Then they say, okay, why don't we integrate these technologies? And right now you see the phones which have camera, so you could take snapshots as well as record videos. You can share this to multiple people, right, using internet wirelessly. Now, what would the future look like? Yeah, maybe flexible screens which you could fold, or you may not. So there is no necessity of having any electronics, just a display board, right, where the information is transmitted, and you could just carry a transparent um, display in your pocket and move around, right? So when you look at this evolution, you'll see that it started off being very bulky because the technology was not there, manufacturing was not there, not much sensors, people had less understanding of what controls were. And then that's why they were bulky, very complex system, because you want to do certain things but not enough technology. It is to be time consuming, right? No control. Every time you have to, for cooking, open the lid and check if it is cooked, or take some of the material out, cool it and check whether it is raw or cooked, right? And then you have to do continuous monitoring. Then in the present, now it has become very simple and compact, right? You could precisely control how much time you want, to what level of cooking you want, and it requires less monitoring. Now in the future, what do you see? You'll get into being more modular, right? Having different functionalities built into it, and this system will learn from the activities which happen over a period of time, adapt to it, get their own control, right? And this will not require any monitoring. Now, when you look at all this, mechatronics has played a significant key role in the evolution of these technologies. And what does mechatronics mean, right? When you have a look at it, you will have a physical device, such as a robot. I just picked this example because it's easier to comprehend, right? You measure few things using sensors, then you actually convert from analog to digital converter. You actually process, look at what sort of controls you want to do, and then convert it back an analog signal, which will be given to an actuator, right? Like an arm, right? And then it is fed back to the device, right? The key thing is to, in this case, it is picking different colors in a particular sequence located at different places. First, you locate the position and color. So there are sensors related to a position sensor, then an image analysis to say what color it is, right? And then there is a distance sensor to say how far it is, right? So these measurements are made using the proximity and image sensor, which are mounted on the arm, and then transmitted to the processor, which then knows what is the target, what needs to be done, how far it is, right? And then it starts moving, providing the inputs to the sensor and the holder, which will then pick up the object, move to the required target location, and place those objects. Okay. So what does it mean? So when you look at mechatronics, it's about a mechanical or physical device controlled by electrical components and need sort of software to make it work, right? So three elements: mechanical, electrical, and the software. We'll come to that a bit more in a couple of minutes. Now, what does it require? So it needs to sense, right? Sense the position, right? Image, position, feel, and see whether it's rough, where it is. Some of those sensors could be acoustic sensors, right? To know what is the vibration and other things. Then you would have different gas sensors to see what is the composition that's coming out, and what is the chemical composition, right? Then you need to take that, transmit, right? And then you actually compute. Then you act using the levers, and then finally you need an energy that is required to do all these processes, right? So 5 things: you need to sense, transmit, do the computation, act, and then you need energy to provide to do all these activities, right? Which essentially means you need different systems that needs to come together to execute a particular activity, right? Now we will see how these have evolved over time, right? So when you look at evolution sense, what has been earlier, the humans, they would see something, oh, it's either here or that location, get a feel of things and then do it. Or they would touch and say, okay, is this hot, or um, is it rough? And then based on that, it used to be. So it's mostly based on the human senses. Then they started including simple sensors like linearly variable LVDTs, differential transducers. There used to be pressure sensors like pressure gauges and all. Then with the advent of uh, precision manufacturing and all, you got into the micro electromechanical systems. Your sensors could be as small as as your nail, and then they started putting them, embedding into the processors, right? So you have all integrated. The feature, how do you see? It's you see this sensor becoming very, very small. So this is where nanotechnology would help a lot, right? So in terms of transmission, there was no signal transmission because there isn't much on sensing. Then there used to be a mechanical transmission of the information, like levers and gears. Then once MEMS and other electronic sensors came into, the transmission has been through the electrical signals, uh, through wires, right? Now you can see it has become wireless. So signals or information, the sensitive information is transmitted wireless. And then now it's more about cloud connectivity, all over Internet of Things, right? In terms of computation, it used to be humans. People has to be trained in this, so they would know what calculations, what are the parameters that needs to be checked, compute, and then decide what to be done next, right? Then with the advent of microprocessors, there are a lot of computation is transferred to the microprocessors. Then the high-speed computations with the speed in computational power. Then it started becoming knowledge-based systems. So you actually provide knowledge to the computer to say, okay, this is the earlier data that we have. So based on this, certain key decisions can be taken. So just use those as a database to make decisions, right? Now, okay, not only you make, you also train other systems. So if one system learns something, it can be immediately transported to others. If it has been humans, right? So humans to train on certain things, maybe it will take anywhere between 3 to 10 years, depending upon how complex the job is. Each individual human has to be trained, right? Until they reach the level of the required skillfulness. But now with machines, if a machine learns something, you can immediately transfer that knowledge and skill set to the other system. So if one system learns, all system learns simultaneously, right? And it doesn't require to again train the system right from the basics. In terms of action, earlier there was no action, right? You let it do whatever it wants. Then it is to be reactive. You go periodically to check what is the status, and based on what you see, you react, and then do the action to either end some things or do the next step. Then it became predictive. Now you build simple models to say, okay, at what time, under what parameters does a particular action reach the required state. So you predict that, and you know based on the time taken and certain parameters that are measured, it has reached a certain point, right? So in cooking, you look at temperatures, you look at pressure built up and other things. Then it got into learn and adapt, right? So earlier it was predict, now it will learn. So there will be, if new parameters come in, how did the system respond? All this data is fed back to the system to make it learn, so that even next time when a certain event happens, it knows, hey, earlier it happened and this was the action taken. Now that information becomes the knowledge of the system, and it will try to do, right? Going forward, you say, yeah, everything will become, most of the things that are repetitive in nature, right, and follow rules can be automated. Energy, earlier, yeah, either humans or animals used to provide energy. Then with the advent of steam power, or using water to run certain mills, right? They used to do the shaft power. Then with the advent of heat engines, we started using diesel, petrol, coal to actually generate the required shaft power, and they use that, and also add generators. Now it has become electric, right? In future, maybe it will become more contactless energy transfer, and more emphasis on renewables. So if you look at the evolution of mechatronics, you are looking at systems that will start to learn and adapt based on what they are trained, and in future what they see. Then you'll see a lot of Internet of Things, Industry 4.0, which is more about looking at autonomous systems, 3D printing, robotics, new materials like graphene and others, and distributed systems. So each one trying to act independently at different places, and later on connected using Internet of Things, right? So where are the applications? So you will see um, appliances. Could look at grinders, washing machines, micro ovens. Um, then in business, you look at counting notes or printing, where it will detect if there is a paper put in. It will sense, is it an image or a word or text, and you actually also can give commands in terms of number of prints, or you want to scan, right? And then you are sort of automate that. Banking, if you go into ATM, earlier it used to be like buttons, then the touch screen came. Now you need not even enter your password. You could, based on your mobile and your account, you could actually dispense the money, right? Healthcare, there is a significant um, inroads of mechatronics into healthcare. Um, the left one is the Da Vinci um, operation equipment, where the machine is to the left, and the doctor is sitting at the back at a console and trying to do the surgeries, which includes keyhole, right? You would have a much better view using the microscope that is built in. The type of needles and equipment that are used are precision and pretty very small bodied, so you could do a lot of keyhole with a lot of precisions, right? So they are almost like close to 5,000 of these worldwide, maybe 1 million of those operations already done. Healthcare, the other application is in terms of exoskeletons. This has a couple of applications. It's like a prosthetics for people or people whose limbs are weak. You actually mount this and then as a band, and use the sensors to detect what action needs to be done, and then use the motors and actuation to provide the required movement. Same thing with exoskeletons in terms of doing or lifting heavy objects, right, with less effort. You can also look at the autonomous UV sanitizer, because if a place is with virus or sudden infectants, so you don't want to go there, so you send a mobile robot which would go there, activate the UV light, sanitize that, and comes back. Then it is safe for people to go in. You could look at agriculture, where people are looking into precision manufacturing, whereby it starts with looking at the integration of climatic conditions, soil quality, what is the sort of water quality, and then decide when to sow. After sowing and sprouting, and when you look at it growing, you can actually go uh, do a visualization of, is it ripe or is it infected, or does it require water, and based on the sensors you could actually go and water it, or if you see some infection for the weed or the weed growing, actually go and spray pesticides, and when it is ripe, right, you could actually reap. Or if it is like fruits and all, you can pick and choose based on the color and the surface texture, whether it is ripe to be plucked or not, and based on that do it, right? So a lot of applications in that. Transportation, this has been the a lot of talk going on. You have the uh, autonomous underwater, where it has been going on for a long time, where people have been using underwater robots to actually navigate, go to greater depths, look at, you know, what is the underwater life is like. And electric vehicles. So the most of the cars have evolved with a lot of mechatronics built into it, which includes moving from mechanical to electric distributors for spark ignition, right? Lighting, your refrigeration, the air conditioning part of it. Then in terms of power steering, you put less effort and you'll be able to get the maximum turning, whichever you need. Then you're looking at anti-lock braking system, ABS, then the airbags, right? Uh, so seat belts, everything is there's a lot of mechatronics in that. Aviation, it has been come to a stage where you could put in autopilot mode with fly-by-wire, and most of the knowledge systems and the electronics, sensors, and everything come together to make it fly. You're looking at drones. Manufacturing, there has been significant activity in terms of manufacturing, the pick and place things evolving, where it started with simple pick and place to actually spraying paints. Or if you are looking at car assemblies, you can see a lot of that being automated, with a lot of precision being done. Then the evolution of the 3D printers. So earlier, the design was, you actually design based on the constraints of the manufacturing. So you're losing a lot of effort. Then you would give to, based on what material is it. It would start with casting. Then it would go through a series of processes in terms of cleaning the casting from all debris. Then it will go into machining. After machining again, it will go into cleaning, right? And then after that machining, then it will go through the other processes in terms of tapping, threading, and others, and then finally you would assemble, right? And if the passages are pretty intricate, then you have to cut the parts into multiple parts so that the internal passages can be appropriately machined. Then you assemble. Now this involves a lot of processes to be done, and it would take almost 3 to 6 months, right from your design CAD availability to actually part. Now with the 3D printers, you can actually see how it looks within maybe a couple of hours or a day, depending upon what is the size and what is the material. So you can see 3D printing, there is no constraint on the design that you come up with. So a lot of designs, there's a lot of going into regenerative designs, where you give the constraints and the design will evolve based on the constraints given, and you could just give that 3D geometry to any 3D printer and it will do. So there isn't any constraint in that. So a lot of mechatronics goes into 3D printing in terms of the control, the leveling, the location, how much of the material to dispense at what temperature, and other things, right? So here is an example of a autonomous UV sanitizer. So what does it features? Looking at it has to be autonomous, because you don't want people to actually be there when this is in operation, because the UVC rays are harmful, right? And if it is moving, no obstacles, should be able to do that. So it needs to recognize it, map places to be disinfected. It needs to detect motion, though, so in case if somebody is around it and moving, it would actually stop the UV rays, UV lights. A buzzer will sign on and all. So what does it require? So you require the lighting, you need a power source, you need a lot of sensors like motion detection, then ultrasonic sensors to check if there are any obstacles in the way. Then you require a LiDAR to accurately map the locations and also process the information to say what to do. And also an app so that you could actually map and navigate it. Now, when you look at the physics that are required to this, right, we are looking into structures, looking into electric motors, sensors, and process those signals. We're looking at processors, what processors are required. Can it process the different information that it comes, compare with the existing database it has, and take the right decisions on what to do next, right? And you need to look at how to manage the energy. So with that in mind, which would give a fair idea of what are the disciplines that go into making the mechatronics course. So you have the mechanical, where you need to understand about design of parts, mechanics, which is the motion of different parts and the relative motion, accelerations, what is the impact of gravity, weight, and others. Then materials, what materials go into it. Manufacturing, what sort of manufacturing are you looking, which would is dictated by what is the precision you are looking, right? Then the actuation systems, which could be either hydraulic, which is liquid based, or pneumatic, which is air based systems, right? To that, you will now need to look into electronics and controls. So need a knowledge in terms of the electronics, microelectronics, embedded systems, actuators, what are the different actuators, sensors, how do they work, is there a bias, how you activate it, how to take the information. Then you get into digital signal processing, which includes like getting all the information from your sensors, processing them, understand what those data mean, and then come out with a control strategy to say what to do next, right? Of course, to do this, you need to have your computer system. Then you have to look at how to automate things, look at data and their structure. You need software for programming. Then look at AI and ML to make the systems learn and adapt, right? And of course, make sure that if you are communicating or transferring data across the internet, how do you make the data to be secure? Because you don't want somebody to actually tap into that information or the path and create havoc by changing the way the systems would work. Now added to this would come the integration part, which is the mechatronics, systems engineering, and robotics. Along with that, what is also required is the ethics, which is very significant, right? Ethics, environment, how does it impact people and our environment, and project management, because if it is not one single discipline trying to do one task, it's multidisciplinary. So you will get people from different backgrounds trying to work on it. So how do you interconnect different disciplines to come out with a given solution in the shortest possible time with limited resources, right? So you'll have electrical, mechanical, and computer science, all three coming together. Now, if you look at in this specialization, what advantages a person who, or a student who specializes in mechatronics. So he would be adept in machine learning, sensors and controls, software engineering, mechanical, and system engineering, right? He could individually go to any of these areas or go into the robotics or autonomous areas where all are integrated, right? Few challenges with mechatronics, because it's a blend of different expertise. The student has to be very nimble. Then look at complex influencing parameters, right? Weight, electromagnetics, sudden change. Can you give a sudden step inputs? No, you have to give gradual, right? And then let the system respond to it, adapt to it, and then you keep changing the inputs that go into the system response. Of course, real-time calculation, which essentially means things have to be done pretty fast. So you need to use the best algorithms and numerical methods where the computation time would be pretty short. Right? What is expected of the students? So they should be able to solve complex problems, think critically, decision making, really important, because you have these multidisciplinary things. You need to figure out which way to go. Designing, learning new things, because a lot of things are evolving pretty fast, which was not there yesterday is available today. Tomorrow it is coming out to be much more smarter, better, quicker, faster. Then mathematics, because it requires a lot of computations and calculations. Understanding how a system or the entire organization works. Then how to evaluate a system, right? So these are the critical things that the students will have to come up while doing the mechatronics course. And it's also for others, but other specializations, but here it's much more deep rooted and requires that skill set. Now, a few institutes that have been offering this course, you have the Purdue, Texas, Colorado, Georgia Institute, Michigan. In India, yeah, the MU Ecole Central School of Engineering is starting this year. There are other institutes like Thapar, Manipal, Amity, SRM, VIT, and Shastra. Right? So I'll just leave with this particular video where looking at how most of these workspaces and everything. Um, so you have to make these public places close. So this was a thing that was built by Professor Deep Seth from our robotics and mechanical mechatronics group. Um, it was like, you know, um, 3 months flat. Um, so you look at the motors which drive forward and reverse. You can also uh, trim the left or the right motor to take it to the required location. It's all, autonomously done. So you can pre-program it and let it go. So it can look at obstructions, it can navigate to different locations, uh, move different floors. And there is a lot of thing goes into trying to uh, first understand the requirement, which is in terms of the height and the locations, and based on that it is tuned. Right? So and then if there are people around, so it will actually switches off and then goes to the required positions. Right. I think that's all I would like to share. We'll now go into the questions and then see if so I'm just looking at the questions that have come up, and would be glad to look at so yeah, there was a question, brief about the college. I think we have been there from 2014. It's almost like 7 years of uh, you know um, an operation. We're looking at um, significant investment in R&D research. Um, May 2021, we became the private university under the Telangana Government Act. Um, so, any other thing? Brief about the college. Yeah, we are located in Hyderabad, Telangana. Nice campus. It's a fully residential one. So there's a lot of scope in terms of interacting with the faculty, um, doing the research works in the lab, which are open most of the times. Right. And in terms of faculty, we have all our faculty have a PhD, and a lot of them have postdoctoral fellowship experience abroad and India. So everybody is an expert in his research area, and we are growing a lot in terms of the research we are doing. So there is a question about mechatronics scopes in India and Europe. That's a good question. So because if you look at the applications that I shared, you could look at starting from appliances, banking, you're looking at healthcare, right? Then transportation, EV vehicles or automobiles. You're looking at aircraft engines. So lot of scope both in India and abroad. And then there is a question is about partnership with industries. Definitely, because we have a lot of MOUs with a lot of industries, whereby we have collaborative projects, consultancies. They even tie up trying to provide technical talks, workshops for the students, right? So there's a question about scope of mechatronics in future. Yeah, like I have shown, it's evolving, a lot of scope, application in multiple areas. There's any system where the job is done by the physical interactions, you'll see that mechatronics plays a significant role in that, right? Indian students getting job, yeah, definitely there's a lot of active industries within India. You could definitely, if you look at automotive, transportation, right, healthcare, lot of a scope in that. Then there is a question about deeper into the course, names of course, core and electives that will be offered to mechatronics, right? Thanks, Pawan, for that. So, like I mentioned in the slide on whatever disciplines that is there in mechanical, you start with the basics in terms of the basic courses of electrical, electronics, mechanical, and others, and then you start looking into the mechanics, then design. Those are the mechanical core subjects. Then we get into the electronics. We have the basic electronics, then the digital signal processing, sensors, controls. Then we are looking at computer systems, AI, ML. So those are the core courses, and the electives would evolve based on the interest of the students, which could be including advanced robotics, right, and others. Okay, so how can a processor size become a nano processor? So it this is a lot of, that's a good question, Nayan. So what key thing it goes into is in terms of the manufacturability, right? So as the manufacturing process improves, we are looking at most of these chips going to the nano size. So if you look at most of these processors, you will see, what is the width or what is the nanometer size of the processors that are built into it and how they are made. It's more about the manufacturing, which changes the number of processors and the speed, which essentially means you will see a lot of very compact and very small processors. So there is a question on practical approach. Yeah, that's a very good question, Andrew. Because most of this, until you bring together all what is learned and implemented, there is always a gap in terms of the understanding. So most of the courses come with a lab component. Some are dedicated lab courses. Some are in terms of mini projects that are given as a part of the course, where the student has to work out in the lab, implement certain code, see whether it works, or implement a particular algorithm to make things work. So lot of practical approach to that. Examples of companies which hire mechatronics engineers in India. Yeah, Syed, this I think I addressed earlier. So if you look at into any of the systems which has electronics and mechanical systems combined together, all of them, right? So I'm interested in pursuing a career in aeronautical sector. Would this branch give me an advantage compared to others? So Abhinav, that's a good question. So it's not clear when you mean aeronautical sector is in terms of is your interest into because the aeronautical when you look at aerospace, right? There are different specializations associated with it, right? So if you look at fluid flow, so it would be an entire career of a person looking at flow over the wings of the aeroplane, right? Or if you look at combustion, gas turbine combustion, right? So people spend their entire career, 30, 40 years, just looking at how to make that combustion better, low pollution. Can it take the ice cold environment coming in and still work? Can you reignite if you're going through a um, you know extinguishing of the combustor or aeroacoustics, right? Most of these combustion flames create slight pressure variations, which cause pulses, which get amplified, and then it actually creates instability in the flame. So there are um, engineers whose whole career is about aeroacoustic interaction with combustion flames. Now, this is one part where, you know, if you take an aerospace, then you specialize and pick based on your electives, you do your master's and PhD into some of these areas like aircraft, outside flows, internal flows, combustion, or heat transfer. The other aspects which comes into is the mechanical and electrical system interactions, right? Which is your controls part of it, which is with the pilots, right? And how do you control? So your mechatronics gets into the people who specialize in mechatronics can actually get into aeronautical or aerospace industry and work in terms of how to control the combustion, the flow, look at the sensors and see what needs to be done, how to trim the fuel and the trail to get, prevent vibrations, or can you take a sudden, lift or a dive, right? Those all are handled by the mechatronics systems, right? So there, yeah, people with mechatronics will have a lot of advantage. Demerits of taking mechatronics engineering, Syed, yeah, that's a good question. Why everything comes with certain limitations? Because this particular specialization in terms of mechatronics is understanding different systems. You will not go too deep into it, but you will look at the interactions and see how to make it better, right? So suppose you are pretty much interested into either the structures or fluid domain, right? You may not get too much depth into this, right? So, and the other one is like it involves a lot of interdisciplinary and system thinking, right? You need to have the ability to look at different informations and connect the dots and then come out with a solution, right? You need to actually train for it. Is mechatronics and robotics engineering same? That is David. So David, good question. So robotics is a subset of mechatronics, right? People who do mechatronics in the undergraduate can get into doing their master's, PhD into robotics, right? By taking significant electives on robotics at the undergraduate program. So robotics is a subset of mechatronics. Postgraduate programs that a mechatronics student can pursue, Naveshri, yeah, like I mentioned, you can get into the mechatronics as a postgraduate program. You can get into robotics, you can get into systems engineering, right? Oh, somebody, Nayan, has this question. Can we say that the smaller the processor, the more it is faster and efficient? No, see, it's about how much can you pack, how many processors can you pack into a single chip, right? So the more processors you pack into the chip, right? So it will do multiple computations. So it has got to do more with what you pack inside rather than, if it is smaller, does it get better? Okay, what else do we have? So there is a question about Ekavardhan, most challenging engineering project. It's pretty generic question. So I'm thinking if it has to be like a mechatronics project, the most challenging is trying to address the exoskeletons or the prosthetics that you put to the and try to interact with the sensory signals from the nerves of the person whose limb or any arm has to be activated to do the required work and make their life comfortable, right? So there's a lot of things that are going in that. So anything, see, outside mechanical systems, interaction with electronics and all are a bit easier or simpler, I would say. The more complicated is when the unknown or out of design factors that come in, right? You start a design with certain basic requirements and any extreme cases that you come, right, that may come across. But as there are always situations where there would be conditions that come up for which people have not experienced earlier. So they wouldn't consider that and then design the system. So when those systems arise, the systems don't meet the requirements of the action to be done, right? So that is something no engineer or any person can predict. So they say, okay, I know all these conditions would occur, and you take that and you design the system. But there are always those cases where it would be beyond your imagination on what would happen, right? So yeah, in those situations, you consider it and see what best could be done, and there were iterations which would happen, right? So you, in any of the projects or any task, right? Over analyzing will not give you a required output, right? So you say, okay, I have this hypothesis, let me build, try, see what I learn, based on the learning, do the iteration, improve the product, and then get to the next item, right? So you learn, you do, you learn from what you have done, iterate, and move forward. That's the best, right? Um, Nanotechnology associated with mechatronics. This again, Naveshri. Yes, Naveshri. So in mechatronics, the key thing is about your sensors and the processing, right? Sensors, how small can you make a sensor? Right now, if you see most of the sensors in terms of in mobile, right? You would have a touch sensor, you have a light sensor, which senses light. You have a proximity sensor, which senses if your phone is near your ear, so that it actually locks the screen such that when you touch the phone to the ear, there is no other action that is being done, right? So earlier, these sensors used to be very bulky, heavy, right? Right now, you can see it's buried multiple sensors, including accelerometers, right? A big accelerometer used to be like 50 by 50 right? Which you have to hold in the hand, heavily fixed to the system, very bulky. Now, with the advent of precision manufacturing and very fabrication of very, very small components, you are getting into um, trying to make these sensors and processors as small as possible. The smaller they are, it becomes very compact, and there are a lot of, you could integrate them on a single chip, a single board, and integrate the whole thing on a single board and assemble like mobiles are done, right? Yeah, it's part of how you integrate your sensors, controls, electronics, processors onto a board. Yeah, it's part of mechatronics. What else? So there are generic questions. Okay, so that's an interesting topic. A coworker believes that design is better than yours. What do you do? So I think if there are no other questions, we can take that. But um, that is something that needs to be looked in totality to understand. Yeah, why do they think? See, design is better or not depends upon what are the requirements, right? You lay out the requirements and evaluate one design against the others, right? Otherwise, people come with their own idea of what their design is good at, right? So the key to that is first put down what are the requirements. Yeah, I need this five. It has five things. It has to be light, compact. It needs to work under these conditions. It should be, this much cost. It should be robust. Its weight should be so less, and all of this should be able to integrate. My service should be good. Can I replace these parts and make it better? In future, can I make this product upgradable by just replacing the component? Right? So you put all those requirements what the customer is asking, and then you say, okay, design A versus design B. You get your experts, ask them to come. So in this, the key thing is to get experts whom the other person believes, right? So who trusts? So you bring your senior engineer, principal, chief engineer, and then say, okay, here are the criteria or the customer requirements. Here is design A, here is design B. Can we objectively evaluate met, not met, to be met, high, medium, low? Then I think that should be done. Okay. Yeah, I know. I just picked that because I'm not seeing much questions on the mechatronics part of it. Yes. Any other questions? So for people who have raised hands, I would suggest please put your questions into the chat box. Okay. Okay. Thanks a lot for taking time to attend the session. I like the questions and the interaction. Please ask questions to understand, right? And that helps a lot. So I also get to know a lot of different thought process and perspectives. So we, as faculty, we typically encourage our students to speak up, because it does two things: whether they have understood, they have assimilated, and or they thinking beyond what we have thought and coming up with new ideas, right? So one last question before we wrap it up. AI related with mechatronics, definitely, right? When you want to train your systems so that they learn and adapt, you need a lot of artificial intelligence that needs to go into the computation part of it, right? Do you need to build only digital models, or do you have a physical digital analytics, right? Where you bring in the physics part of it, of what the system is about, and the rest you use based on the information you get from the sensors, right? So AI definitely with mechatronics. Yes. Okay. Thanks a lot for joining this session. We appreciate you joining. Keep the questions, and I think our admissions team, you have the contact, so you could contact them. Okay. Bye for now. Take care. Be safe.